practical, what people used in practice is that once you provide it with data sets here, and I don't know which one is training, which one with testing, but I know the data sets here came with labels, came with annotations here. And now I have several candidate learning models, algorithm, and I want to pick up the right one, the best one. What should I do? Well, and what people typically do is this: I can split the data into a chunk for training purpose, another data for testing purpose. And we call this type of data called training data if it's used for training, for learning parameters of the models. And the second set of data, we call it test data, if it is used for evaluation of the models, right? And then once you split your data, typically randomly split them into training and testing. And if you randomly split them here, and we hope that distributions of the data here roughly is similar to the distributions of the test data sets. So we assume they are pretty shared similar characteristics. So now what you can do, you can learn your models on the training data, learn all the parameters of each model on the training data, and then you can evaluate all models on the test data, and then pick up the best performer. And that's many people do, and that's very common practice. However, this is actually a flawed approach. The problem is that whenever you pick up the best models here, best performance here, so that best performance here is based on the evaluation on the test data sets, right? So because your model is picking up based on test data set here, that you introduce some bias to your models, right? So you overestimate the performance of your models because you have 10 models, you just pick up the one that fit better. So even if all the models have equal performance on potential test data, because you pick up the one that is best performance, so that lucky model turns out to have best numbers, but doesn't mean that that number can generalize to actual test data sets. So that is a potential bias introduced into this approaches here. So for this purpose here, we should emphasize that this is a kind of guidance people always follow, is saying that your learning algorithm should never ever have access to the test data sets. Whenever you try to kind of evaluate the performance of your models, what do? You can split your data into training and testing. And then in the very beginning, you hide your test to somewhere else, right? And then whenever you pick up the model, including training your models and comparing different models, pick the best one. And the entire procedure here should be agnostic to what type of test data you have. So that's the key guidance. And if under that guidance, this type of approach is not going to be valid. So because there's a potential bias introduced here. So instead, what we can do, now comes to the actual practice. What people do is this: once you have data sets here, and we can split the data randomly into 3 piles of data. One used for training, and those are used for learning the parameters of your models. And then you have your test data sets for the final evaluation purpose. And then you left this data set hide somewhere and you don't see them throughout your training and model selection process. However, you're going to have reserved some data for validation. The purpose of this validation data set is to select the best models. And the idea is that, well, so now because you have this validation data set available, what you can do, you can learn each model based on training data sets. And then among all the models you already learned, and then you can evaluate the performance of the model on this validation data set. And then you can pick up the best performer. Once you pick up the best performer, and then you can evaluate the models, the best performer on the test data sets. And that is going to be more objective evaluation performance evaluation. And that usually can generalize well on the other unknown test data sets. So that's the practice. I highly encourage everyone should follow this type of a kind of a split of data into training, validation, and testing, 3 split here, done randomly. So however, there's of course, when you do this type of splitting here, you have some potential issues. So one issue is this: you actually lose some of the data, right? Because some of the data, initially, I'm trying to use all the data sets for training my models. However, because the reasons I need to choose the models based on some validation data sets, and I need to evaluate the performance. For that reason, once you split them, and those data sets here, the validation and test cannot be used for training your models because you kind of put that aside. And of course, and we all know that in machine learning, the data is extremely important. The more data you have, and then there are better chance for you to come up with the better models. So, so for this type of splitting here, there is a potential issues. You are losing some of the data for training purpose of that. And because you are training your model based on a smaller number of training data sets, and you might be introduced kind of more bias into your models because your models are now kind of trained based on smaller data sets. You have less opportunity to pull away from the underlying assumptions or bias of that. So that's kind of a potential kind of disadvantage and of the splitting of this data set into these three parts.